microphone. Thank you. All right, guys, so let's see. All right. Okay, here we are with the notes. So first, how are you guys doing? I'm good? Even with my wife's Colombian, they call it pendejadas in Colombia. It's not as bad as Mexican pendejadas, but Colombia just means foolish behavior, so that's what I've been up to. So everybody's stress levels down? No? Stress levels high? You know, I was driving, I don't get out of the house much anymore. Last week started going back to the office. But, so it gave me a chance to, when I was driving over to Cal Poly, it got me a chance to reminisce about the good old bad days in the undergrad program at UCSD. And I was driving my wife over, and she went to school here, got her master's here. So she was having flashbacks with the bad old days of going to Cal Poly for master's. I was telling her about my experience was sophomore year. I remember parking the car in the parking lot, and then walking over to the library. Halfway through the library, I stopped because I got a panic attack because I realized very clearly that I was not going to survive that semester, and it was a quarter system. I wasn't going to survive that quarter. I was going to make it. It's like being a drowning man in the water, going shore's too far, and now I'm realizing it. I'm not going to survive this quarter. I'm not going to get my degree. What am I going to do? It's like on the way to the library to study, and it was like a real visceral feeling. And it's one of those things like it's, I'm an old dude, so it's like, imagine how many years have gone by. But I do remember that time. So anyway, I did manage to survive the quarter. I got my undergrad degree, went to grad school, got an engineering career, not homeless, have a car, so have a dog. So anyway, I'll be all right, guys. So anyway, if you're stressing, I know. I'm like of two minds what to, I'm in a weird situation here. I'm not a professional teacher by any stretch of the imagination. Far from it. I think I introduced you guys, I'm from the industry. I just sort of vaguely remember what it was like being a student. So, I'm in a weird situation here. I'm teaching you guys. You guys are the students. I'm not a professional. So I wonder, what to do with you guys. Right, because I'm bearing my soul here with you guys. So what to do with you guys? Because I am both a very sympathetic guy, nice person, and I have these memories of these horrible days. But at the same time, I really believe in negative feedback and putting yourself in tough situations and hammering your head against the wall, being defeated and learning from the experience and getting tougher. Okay, so you guys might have a Mr. Was it Dr. Hyde, Jekyll, Mr. whatever. Anyway, so this kind of this thing, because I'm trying to do, believe it or not, I'm just here to do my best for you guys. I'm not a teacher. It's not what I do for a living. I'm here for you guys. But at the same time, I'm here to abuse you guys, hopefully for good reason. So it's a little weird situation, right? So anyway, we'll go as time goes on. So hopefully, I'm trying to still figure out where to push, where to pull back. But anyway, just wanted to let you guys know about my thinking. If I seem excessively cruel or excessively kind, I'm still trying to decide. All right. Okay, having said that, so where are we? So we're in electromagnetics, right? The other thing I wanted to tell you guys is this about electromagnetics, right? So I'm lecturing to you guys. And like I mentioned to you guys, I love E&M, just from memory of taking E&M. And I've used it over the years, obviously. but not like on a daily basis. Wasn't doing surface integrals and curls and divs and whatever, right? So I am also going through, as I'm teaching you guys, making the lectures, I'm also going through and remembering how to do the curl and the dot product and surface integral and stuff. So if you guys are having a hard time with it, just chill. I have to go look up what this integral solution is, how do you do this secant. I had to look up secant, what it meant, right? But what that integral is, you'll have to do the same, okay? It's just the nature of the beast, and just look it up. I'm doing the same thing. It's not like I'm lecturing to you guys. I've prepared lectures, so I'm like, oh yeah, I do the substitution. Nah, I gotta go look it up. So that's one. So don't amp out about that. But there's no way around it either, okay, for an E&M class about doing these surface integrals and divs and curls, etc. The major thing you have to, I'm not saying you don't have to do that, but I feel the major thing and what's really stayed with me is the concepts, okay? Concepts of charge, electric field. Like before I was teaching classes, I would be having, arguing about electromagnetics with my buddies over a couple of martinis in a nice bar. That's like how deep it is in our, arguing whether the electric field has to terminate on a charge or not, believe it or not. So these are the concepts you guys should get comfortable with as much as you can. But again, I'm not saying the math is not, math is unfortunate. It's not unfortunate. It is just what it is, right? But you'll struggle with it if you're staring at some surface integral or some vector problem. I'm doing the same thing, okay? So, but the answers are there. It's not like E&M's been around for a long time. So anyway, just sort of the word of, hopefully, I don't know if that helps you guys or not, but anyway, so okay, so let's do a quick, first thing I was gonna do is, one problem with teaching once a week is I forgot where the heck even, what we were doing. So I keep going back to, let's see, how can I get comfortable here? Let's go all the way up. All right, it's cool. All right, guys, so let's do a quick review. What did we, so today we're gonna learn, so we did Coulomb's law. Now we're gonna do Gauss's law today. Well, first, so let's review some of the concepts, okay? So one, the electric field. And to remind myself, I wrote in my notes the notion of an electric field. Okay, because as I was telling you guys, my latest thinking is just it's just a notion. It's a notional thing. Okay, and here's the idea. If you have, let's say you got a bunch of charges sitting around. So I got a couple of plus charges. So this is Q3 minus charge. And you're thinking about a particular location here. So the idea of an electric field is you're asking yourself, what would happen if I put an electric charge here, or here, or here, or here, 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 here. In a case of Coulomb's law, without the concept of electric field, there's a sort of a receiving electric charge somewhere that's receiving that force. So you're only defining your problem in 2 points in space, whereas electric field as a notion is telling you what's going on theoretically in the entire universe caused by these charges that we have. And then you can think about what would happen if some charge lands there, or there, or there, or there. And so you can kind of easier to imagine movements of charge, et cetera. And the way basically it comes out, so if you think about the electric field here, by superposition, I missed a line there, but by the way, you always think of the test charge as being positive. So when I'm drawing this, it means that this guy's gonna push it away, this guy is gonna push it away, this guy is gonna pull on it, and you sum all those vectors, and in this case, just I think these two pluses are closer. You have a vector here, and you have a smaller vector pulling back. So you probably get something like that. That's going to happen to that test charge. So that if you put a positive charge here, it's going to get pushed in this direction. Okay. So the force of that charge, force on that charge is going to be the Q times the electric field. And I want to keep screwing up this vector notation, but remember we've got vector notations because we want both amplitude and direction. And this is the same as Coulomb's law. Okay, so Coulomb's law said, it's just a different way of writing it. If it was Q1, Q2, 4 pi epsilon naught, 1 over r squared, or E sub r. And all we did was we moved this Q2 guy, whoops, out of here. What am I doing? And so that we could get this notion of electric field. And we called this first half electric field. Just so that we have this ability to have a tool that's easier to deal with in terms of thinking about forces being everywhere around us, okay, except not just at like this particular instance. Okay, and obviously, I don't know if you guys, I guess it goes without saying that electric field, like the concept is extremely important to everything we do in pretty much every field electrical engineers are in. In fact, if you don't get into semiconductor, like solid state physics, I'm trying to think of like for EEs, right? So if you don't get into solid state physics, you're not talking about quantum, that's where you talk about quantum physics, until you talk about that point. And, I guess maybe like, I don't really understand it very well, but I think GPS system, satellite, they use some concepts of relativity to fix, there's some errors there. But besides those two, E&M basically is all you need is for all electrical engineering, is all the physics you need. Okay, for all of anyway, and majority of that in my mind, there's electric field and there's magnetic field. Electric field wise, so the electric field concept is notional, is a concept, but it's extremely powerful, okay? And you'll see the power, and you'll be talking about it in all your classes and all your work, et cetera. Okay, so that's the electric field. Now, the next concept is that it's useful to have some way to visualize the electric field, okay? Just like you have a map that visualizes what, LA traffic or LA looks like, right? So we have this method of people have come up with, which is if you have a charge, for example, you put these electric field lines, and you basically draw lines, and this is your decision how many lines you draw, but basically you have draw lines that show the direction of the force on a test charge. So if I had a positive charge here, then let's say I was going to draw 8 lines. Okay, that would go there, and this direction, these arrows on these lines would show where a test charge would go. If I put a test charge here, it tells you to shoot up that way, go here, shoot up that way, shoot up that way. And so this is just like a visual map, okay? So that tells you where the test charge would go. Again, a positive test charge would get pushed towards. And then the density of these lines tell you how strong the electric field is. So for example, if I draw a surface here, imagine a sphere here. And by the density, I don't mean like the density of like a solid density. This is the density of a line's crossing an area. So imagine if I had like a tiny board. Imagine if I had like a tiny board here and I was just counting on how many of these lines I've drawn cross it. That's what I mean by the density. It's like the density is, so density is, equation is number of lines per unit area that's crossing. Okay, so if I, I would just sort of divide this into different places, but if you imagine if I had a solid area, so like a solid sphere here, okay, or a sphere here, the area of the sphere is much smaller than the area of that sphere, but they have the same number of lines that are drawn going through them. So the density is higher here than here, okay? So it represents that the electric field is stronger here than here, okay? And the reason this is useful, or, something like it's useful, is that, if you think about the area of the sphere, okay, the area of a sphere is is 4 pi r squared, right? So the area of this guy, if this is r and this is 2r, okay, the area of this guy is 4 times bigger, the area of this guy is 4 times bigger than the area of this guy, and it just so happens the electric field is dropping as 1 over r squared. So this is like a useful, again, if it's a visual tool, right? Okay. So it's a visual map of it. It's very useful. Again, seems like we're just kind of doing stuff with like equation math, whatever. But again, as you flip through books, you see these electric field lines drawn everywhere. Okay, so, and then the number of lines that we draw, like I just drew 8 lines here, this gets a little confusing. Okay, so the number of lines just depends, it's just a made up thing. Okay, as long as it's symmetric. You don't want to have like 3 lines up here and 5 lines down here. Okay, because if you rotate, I got a charge in the center in this particular drawing, right? I got a charge in the center, so if I rotate the charge, there shouldn't be any asymmetry in the electric field. So you just have to make sure you're keeping that in mind. So you have to stay consistent with the number of lines you draw per coulomb of charge. Okay, so, but the number you draw, it could be 8, could be 12, could be whatever, but you stay with a consistent number of lines per coulomb. Okay, so if you're sitting there drawing by yourself. So this is, again, a concept. But just like if you chose, in like a day-to-day life, we choose inches and centimeters to measure distances. We could easily pick, I don't know, parsecs and light years to tell the distance between me and you guys, right? But it would give you some nasty calculations and numbers if I'm trying to just think about how many parsecs I'm separated from you. Well, I don't even know what a parsec is, but you know what I'm saying. So by convention, what people use, and this is, you do not draw this many lines, again, this is like sort of visual, is you think about drawing, this is by convention, and you could choose not to go by this convention, okay, but it makes life a little easier when you do the calculations. By convention, you draw 1 over epsilon naught lines per coulomb. And that's a humongous number. So now, like, I'm not going to draw one. Like, we'll be here for the age of the universe if I try to do that. But think about this. So again, the density is number of lines per area. Okay, that's what we mean. So if you think of a sphere, it ends up being number of lines per 4 pi r squared. Okay, so if I use this many lines per coulomb, okay, I am going to have, so if I have a charge q coulombs, I would do that 1 over epsilon naught per area for pi r squared, and that gives me the actual electric field, which is this guy. That's kind of a convenient thing for doing math, okay? I mean, I could have picked 5 over epsilon naught lines. Like 5 times as many lines, it would have given me 5 times the electric field, but it's a little inconvenient. You know, I just want it to be the electric field. Okay, and this seems a little weird, but I think as we do the calculations, maybe it'll be a little bit, go ahead.
In reality, isn't there an infinite amount of lines coming out of a point charge? And then if we did that, wouldn't the density always be the same because it's infinity divided by a number?
Infinite number. Now think about it this way though. The whole concept here is a map. The number of lines is just is a concept. So I see where you're going with that, saying, well, the electric field is uniform everywhere, but it kind of like makes the map idea fall apart. Do you see what I'm saying? It doesn't fall apart. It just becomes not a useful model of how you're going about things. I don't know how the analogy would be to an actual map, but
Polygon map that have too many lines too.
yeah, maybe it'd be something like that, where you have something that has basically it just looks like a topographic line with like just everything's sort of dark because all your topographic lines are continuously drawn and it doesn't really help you. But think of the map as is like a tool to get you, and so what you're trying to do is to have situations where you're showing, like you have this electric field you're trying to represent in this map as a visual aid, okay? And it has 2 components. It has a direction and it has an amplitude. So that's kind of all the use of this map, is trying to give you that visual idea that, hey, like things are stronger here than here, etc. So now, like in a point charge here, it kind of goes without saying, right? You know it's stronger here than there, again, as a visual tool. But in more complex situations, it helps to just have that visual. So all you're using sort of the map for, in my opinion, is you're kind of like looking at it and go, like for example, when we get to transmission lines later on, and transmission line is something you use if you're doing digital circuits or printed circuit boards. I mean, this is where the rubber meets the road, or doing RF designs, right? The rubber meets the road from an E&M sort of direct usage activity. You'll basically be looking at like the electric field lines and going, okay, you know, this is an issue. Or if you're looking at parasitics in a chip design, which is something I do or used to do for a living, you're looking at electric field lines going, okay, they're too dense over here. This thing is not going to be good. It's not going to be happy. It's going to break down. So does that help?
Yeah.
Yeah, you can't. I guess it's not like a literal physics concept. In fact, this is weird. So I had not thought about this before I was preparing my lectures for E&M, but we have, as I was trying to get to when in our first lecture, humans, as far as I know, we, as smart as we think we are and as good as our physics is, we have no direct measurement of force. Like nobody's ever measured gravity, okay? The only thing you can measure is if I have something with a mass, it moves like I was trying to say. Once you see acceleration, you say, oh, there's a force there because of the equation. Force equals to mass times acceleration. But nobody's actually measured gravity. Well, people are trying to measure gravitons and whatever. But nobody's ever measured an electric field. You're measuring, I know this is very disturbing and a strange concept, right? We're measuring proxies. Okay, we're always thinking of these things as what effect they're having on particles with mass. Okay,
Well,
so
mass is arbitrary too.
Ma-
You
the-
just have that 1 kilogram thing
Yeah.
that's protected.
yeah. I mean, it's like an arbitrary unit of measurement, but like you're not going to get any force. Force is not going to be effective on a photon, right? But you need mass. But anyway, I'm just saying, like, so many of our concepts are notional and models of how it works. You know, it's tempting to push them too far, but like, just, you know, don't push them too far. Break down. The whole thing will break down. Then you realize it's all made up, and the Earth is flat. Okay. All right. So, electric field, notion, lines. By the way, is this going okay, guys? I'm worried I'm boring you guys or whatever. This is like good for me. Hopefully it's good for you guys. This is like jumping into, transmission lines without having a good solid feel for this stuff is not going to be useful. Okay, so then we talked also about the concept of a dipole, a notion, which will come back to haunt us from time to time, and as just as an illustrative thing. And that's the dipole is you have two equal and opposite charges, a certain distance a away from each other. Okay, and we talked about that this has, if you look at, there's well-defined electric field lines. If we had an infinite amount of time, I guess, hope you guys can see that we could just sit here and calculate. I mean, at every one of these points, basically you're calculating the effect of this guy on this. Whoops, I should draw that vector a little bit more carefully. On this test charge here, and this negative guy is, pulling the test charge strongly here, and so, this is going to look like this, the sum of those two vectors. And if we had enough time, thankfully we don't have to do this because this is sort of a popular thing. You could just sit there and calculate vectors, right, and get all these things on a dipole. By the way, before anybody asks, because it always comes up, is if you're directly on this line and only in that line, you'll get pushed straight out, and that's the only place. Okay, everywhere else, stuff's going to come circling around on a dipole.
Pulled straight in on the other side.
What's that?
Pulled straight in on the other side.
This one? Yep, thank you. Pulled straight in. Thank you. Okay, what else do I want to say? Okay, and then, what we calculated, so the electric field was that it is, interestingly enough, for a dipole, it's something on it's something in, I should say amplitude, just amplitude. Something on the order of 1 over r cubed, r being the distance away from the dipole. And this is a little bit surprising, and we'll see lots of surprising things like this because, you're thinking about Coulomb's law. This is 1 over r squared as a unit, but you're starting to see if you have more complicated geometries, even as something as simple as just two charges, you could end up with something else rather than 1 over r squared. Okay, and then we define something called a dipole moment. Dipole moment as being 2qa. Okay, so that was just a reminder of the dipole. Fourth thing was So we did this thing with the this positive and negative charges as an example. With the electric field lines, we said, okay, what would happen if we put something with a certain velocity going through it? And we did some calculations with this thing dropping off. Because, you know, the electric field is going to give it, it's only in one direction, it's going to give it acceleration, kind of like gravity. Okay? So now what I want to talk about this for a second, because, you know, I was putting in equations with like distance and acceleration and velocity. You know, we're not mechanical engineers, whatever, but the main concept to me of this example is what we just talked about, that you cannot forget that after everything is said and done, what we're talking about is force is equal to mass times acceleration in the end. That's what we're measuring. And here's an object with a mass, okay? And that's how any of this is how any of this stuff works, is you have something, but by the way, it's not sufficient that it has mass. It has mass and it has a property called charge. You could have, if this thing was an uncharged object, it just sailed right through here. And, you know, let's say if it was an atom, that, you know, if it's an electron, it's got charge, it's got proton, it's got a certain charge, or a net charge, okay? But most things in the universe are neutral, just because they have equal number of electrons and protons, so they're just gonna sail right through. If you have mass and you have this thing called charge, which means you have an excess of electrons or protons on you, you'll get affected by this force, okay? And so basically acceleration is Q times the electric field, and remember this is the force divided by mass. I'm just moving stuff around. So this is where the rubber meets the road, okay? This is what this stuff does. Okay, then we talked about, this is the dipole in an electric field. Like we said, okay, if you take this, like let's say if you had two parallel plates with like a constant electric field, and you put, somehow you put a dipole here. Let's say you had a stick, and you somehow glued a positive charge in one end of the stick and a negative charge in the other. What would happen? Well, it turns out that, you know, you get a force on this side from the electric field pushing it this way. Okay, QE. So this is just, this E field is constant. And then because this guy's negative, so this guy's pushing you in this direction, this guy's pushing you in this direction, it's minus QE. So this dipole, like imagine I had charge the either end of this thing glued, positive and negative. It's not going to have any movement this way, okay? But it is free to rotate, so it's going to have it's going to have a torque. It's not going to have a dipole if I put it, so this velocity, this charge is going to move, right? But a dipole is sort of like, on the average, is being held this way, but there's nothing keeping it from rotating, and it's going to have torque movement. I'm very uncomfortable with torque. I don't know how you guys are with torque. It's just, honestly, it's like a rotation and a mathematical concept to me. So I don't think in terms of torques, but basically what it's doing is you are saying, okay, well, things aren't going to be moving in this direction, so I'm only going to think about the component of the force, okay, in this direction, okay? Because imagine if this thing is sitting at an angle, okay, so this is how I look at it. I don't know if this is the appropriate way to look at it, but this is how I look at it. It's going to have a component of force pushing it in that direction, and we're saying that's net zero, okay? But there's going to be a component of force that's going to give you sort of rotation and try to flatten this out. And this gives you, so you have this theta. So you're going to have a torque that's going to try to straighten this out, okay? So, and that ends up being, so 2 QE a sine, sine of theta. And I think one of you guys at the end of the lecture asked me about the sign of this thing. I don't know, I remember who it was. Anybody remember? So this does have a negative sign, okay? So if I think of the actual torque here, it's gonna have P. This is, by the way, this is like this sort of cross products and dot products and stuff that like I have to go look up as well as you guys, so don't feel bad. But anyway, basically indications of where the torque is moving, pointing at, etc. So it's P cross E and a negative sign, okay? Because the negative sign is because the torque, the way to think about the negative sign is this torque is a rotational force is trying to like reduce this angle theta. Okay, it's not trying to increase the angle theta. Okay. So I think this is where we stopped last time. So now I think I just mentioned, I think it was some question of like, we were talking about what would happen under some circumstances with this thing. If, for example, if this guy is sitting here, so if this guy was sitting here, it would have maximum torque, right? If this theta was 90 degrees, right? You got the sine theta here, so it's 90 degrees. You would have the maximum torque, so it'd have the most energy to push you down this way. If it was sitting here, so with the positive and the negative, it would have sine theta would be 0. So there would be no torque on this thing. Okay? And if it was the weird situation, if it was sitting like this, there would still be no torque on this thing, right? Because there's no, in that case, there's no electric field pushing it this way. This is sort of sitting here like that. But it's an unstable situation. Because if you have any kind of like variation, if you're sitting there, if you're like slightly, for whatever reason, you nudge over, you're gonna get like a huge amount of force on you to flip. It is a preferential direction. Okay, so that gives us the direction of potential energy. I think we're gonna call it voltage at some point down the line, etc. So it's a chance for us to talk about that. Okay, so let's talk about that for a bit. Okay, so first, thinking about it like as a mechanical system with a spring. Okay, so you can think of when you're pulling a spring and holding it. Okay, there's force, and then that's related to something called potential energy. Okay, so let's think about that. So for a spring, so I'm going to do we're going to talk about potential now, but first I'm going to do a tangent, talking about springs now. This is tangent, fork. All right. So sorry, sometimes I meander in my discussions, but hopefully it'll make sense. Okay, so for a spring, how are we doing on time? Good. Okay, so the force is minus kx. Okay, so if you had imagine if you had a mass sitting on a spring here, this guy, the spring would have some force equation, something k, like some strength k, and as you move this x away, if you let it go, it's gonna that thing is like exerting. It's gonna give this thing some acceleration as a function of this k. Okay, so there is a definition of potential. Okay, which is U is well, let me put it this way. So force is minus du dx. Okay, so the way this, then U is a potential energy, or potential, okay? So the way potential is defined is as minus integral of force as a function of x. Okay, that's just the relationship between force and potential, okay? So, so if you look at this, in this case, potential is going to be 1/2 k x squared. Just this derivative integral relationship between force and potential. Okay, so what else do I want to say? Okay, so let's think about it if we were just thinking, again, don't necessarily think about electric fields, although it applies to that as well. So think about now is this relationship going back to this guy. If we just use this concept of this, right? So this is for a spring. This is for everything. Okay, this concept of force and potential having this relationship. Force being a negative derivative of the potential, and potential being the integral of force. Okay, so look at it. Let's look at our dipole case. Okay, in the dipole case, because we're talking about torque, okay, and angles, we are basically, thinking about force being sort of equivalent to torque, or that's sort of the rotation, I guess is rotational version of force, I guess you can think of, and x sort of being theta. Okay, so the substitute. So if we were going to think about it in this term, so u is minus f dx. If we were looking at the potential, so from if you're sitting at some angle theta minus, the lowest energy state, which is 0 theta, would give us the integral from 0 to theta of tau d theta. So I'm like, this is sort of equivalent to, I shouldn't put squiggly line. So equivalent to force. So what I'm doing is I'm just writing this. Okay? And notice I put, I don't know why I did this, but this negative, okay, is giving me, did I screw this up already? Yeah, I think this should be, I lost this negative sign here, maybe. I think it's U0 minus U theta, because I got rid of that negative sign. Okay? Now, we have this definition of this guy, okay, with this guy being P, this guy being that, we just called it P, the moment of the dipole. Okay, so it's PE sine theta with, and it has a negative sign, sorry. The negative sign, again, comes from because this torque is trying to reduce the angle. Okay, so I got this negative equation. So let's stick that in here. Ends up being 0 2 theta minus PE sine, oops. Am I doing this right? Theta d theta equals to PE cos theta minus PE. Okay, so it's just that, that's just the solution for sine theta d theta equation. Okay, just the integral, you gotta remember the integrals, sine theta and cosine theta and all that good stuff. Okay. Isn't sine theta d theta integral of it is minus cos theta? Am I remembering this correctly? Say yes. No. Anyway, I have to look it up. So that's U0, oops, u0 minus u of theta. What else do I want to say? So if I just look at u of theta, which is this guy, sorry guys, I'm writing this. So this should be 0. I write my zeros and thetas like very similarly. So u of theta is equal, if I like look at this, and this is minus PE cos theta. And this is the same as u of theta is minus P dot E. Okay? So torque, like you're thinking about it in terms of force, is minus P cross E. And the potential is minus P dot E. Okay, dot product, cross product. Okay, so as usual, I was trying to think about what that dot product means. And sort of what dot product means is it's trying to, let me get this right. What dot product means is it's trying to say how close are two things to be facing in the same direction. Okay, so if you have two vectors, if you look at their dot product, gets bigger as the two vectors are sort of facing each other. Just a function of like the cos theta. So if you want to think of it visually of what a dot product looks like for two vectors. Okay, so torque is a little bit harder to think about because it's sort of pointing in a perpendicular direction to the two. So I couldn't get my head around the visual of that, but the dot product is a little easier. It's trying to give you an indication of two things that are two vectors that are pointing in the same direction. I don't know if that's helpful as a visual for you guys or not. Okay, so but let us come back to this is the potential and you had the torque. Okay, so let's draw this thing. This is going back to the last thing I drew for you guys, I think, in the class. So I drew for you guys this theta. So I sort of made a graph of P dot of this guy. Okay, so this is the potential of our dipole. Okay, so at zero, cos of theta, so over here, remember 0 is what? 0, theta is when the thing is just pointed with the positive is the electric field. Where is it? 0 is like this, the positive here, negative here. Okay, so that with our little equation here ends up being minus PE, right? Cos theta is 0 is 1, got minus PE, so it's like down here. Okay, at pi, so at pi over 2, what's pi over 2? Pi over 2 is when, whoops, it's, this dipole is sitting like here. Okay, so it's 90 degrees for theta. So at that point, cos is 0, going to be here. It's got a cosine function. And at pi, goes up like this, it becomes cos of pi is minus 1, so I end up with plus PE here. Okay? So you could think this is called, so this is, I love this nomenclature. So this is when the dipole is parallel to the electric field. But I always root for the anti-parallel guys. The dipole is anti-parallel. This means just that the thing is sitting with the, again, it's sitting like that. Okay? So now this is the u of theta. Remember that tau, the torque, is the derivative minus derivative of u, okay? So if you look at this point, so this point, you're looking at the slope for torque. This is the point of maximum slope. So you're going to have the maximum torque here. Maximum, when this thing is sitting like this, you're going to have the maximum torque on it. Okay, here, because I'm taking the derivative of this equation. At the parallel point and the anti-parallel point, so if you're sitting like this or like this, the derivatives are 0, means you have no torque. There's nothing rotating that guy. Okay? But, again, the visual is, if you think about this as like a hill, if we're talking about like a pebble or something, not pebble, but I don't know, whatever, a marble on a hill, here or here, there's no torque on this thing. But here you can think of it about this thing being in a, this goes, by the way, like this, minus pi over 2 and so on. So here you can think of this thing sitting here. If there's a little bit of disturbance one way or another, it's just sort of rattling around here. Right, just gonna do that. Here is not a stable scenario here, right? So you get a little bit of rattling, it's just gonna roll all the way, the thing is just gonna flip like that, as long as there's a little bit of movement on it, okay? So again, this is like, we're talking about dipoles, we're talking about, you know, how things are moving around, but we're also introducing this concept of potential versus force. Not versus, but that relationship. Okay, that's gonna come back. And in the end, that, you know, potential is gonna be something you're gonna be dealing with more than electric field. In my daily life, that potential is voltage. Okay, that's kind of like what you kind of measure usually, as opposed to electric field. Sort of electric field, you do designs with potential, you kind of, you're not measuring it directly again, like I said, but it's like, you know, your voltage, your oscilloscope is measuring the potential one way or another in the form of voltage. Okay, so that's where we ended up. Wanted to finish that up. Okay, so now is the time for the dreaded time of example calculations and vector summation and integrals. So, would you guys like a break now for about 10 minutes, or would you like to do it?
Yeah, let's do an example or two first.
Huh?
Let's do an example or two first.
Okay, let's do an example. All right. All right. So, example 1. That's a hint there's more examples to come. So, okay, the first example. Imagine if you had a plate with positive charges, and it's an infinite plate. Oops. Sorry, infinite line. It's not a plate. Infinite line. So, it's an infinite line. This is a very important statement, infinite. And its charge is uniformly distributed along it. Okay? And I want to find the electric field out here. Okay, so now, again, models. There's no such thing as uniform charge, right? Charges come in units of 1.6 times 10 to the minus 19. They're discrete. But for the sake of this problem, I'm just going to call uniform density of charge. Okay, so we're going to think about like there is a charge. So it's basically lambda coulombs per meter, say. Okay, of charge distributed here, and it's infinite. Okay, so if I was going to look at this, so this is like looking at it like this line, looking at it like this guy. Okay, so if I was going to look at it like this, just be, you know, a line coming out of the, oops, it'd be coming out of the, like, you know, if you're not careful, you're going to poke your eye out, kind of thing coming out. So basically, when we're looking at electric fields, I'm calculating the electric field here and here, say, right? But if I look at it here, I'm calculating the electric field all sort of around, okay? So keep that visual. So now let's think about it. So you're putting in your test charge somewhere here, okay? So as usual, we're faking this problem, so it's a little bit easier to solve, okay? So why did I say infinite line?
So that it's absolutely even on either side and it cancels out the x-axis.
Exactly. So basically for every thing, so for every, those are my test charge, for every guy sitting here, lambda dx, if you can think of this as sort of a unit of charge that's pushing this out this way, there is his sort of evil twin sitting here at this other side. So let's say this is my axis, this is 0, x equal to 0. And this is, x goes to plus infinity, and this x goes to minus infinity. So there's another guy here that pushing it this way, right? So that exactly cancels out this guy with this guy. So the only electric field I have to worry about calculating is one going in this direction. Okay? So I'm faking this problem to make it life easy for us to do vector calculation. Okay, what is the other stuff it does? Well, the other nice thing it does for us is as long as this distance, let's call this distance A, as long as this distance stays constant, the electric field is the same here. So if I was a drawing line here, all the way around, because imagine if I don't know, by symmetry or whatever, if I nudge over by a little bit, it's an infinite line, so the line's going to look the same to me. If I'm a meter over one way, 2 meters over the other way, a light year over this way, a light year over there. So these are like, as long as stuff is a particular distance away from this guy, it's going to have the same electric field. Okay, again, makes life a little easier. Okay, so what else do I want to say about this? Okay, so now let's look at this thing, right? So we've got an axis we've defined. So we've got this x-axis. And let's say we're looking at this. Again, I'm doing this at x equal, putting the charge at x equal to 0, but I'm making a claim that it doesn't matter x equal to 0, x equal to 1, minus 1, whatever. It's all going to come do the same thing. Okay, and so at some distance x away, I'm going to have a chunk of charge sitting here that's lambda dx, where this thing is some infinitesimal area, not area, some infinitesimal length. That's what the dx means. It's really, really tiny, right? And then at minus x, whoops, at minus x, I've got some other infinitesimal thing, lambda dx, okay? And because it's infinitesimally small, I can just treat these like point charges. So I'm going to treat this as like being a point. So the lambda dx is the amount of charge in that infinitesimally small length as a point charge, okay? So there, I just think of that as having an electric field component going this way, his buddy having an electric field component going that way. And so this component and that component, they cancel each other out. And I only get left with this guy. Okay? So I keep emphasizing weird things, but it's because this is exactly the kind of stuff that confused the hell out of me when I was set me in these weird loops. I'm just making up these problems So it's easy, like I'm trying to like create situations where I can ignore stuff and only do cos of theta or only do sine of theta angles. This is not like some universal idea, okay? So faking a problem so we can sort of do some simple calculations. Okay, I don't know, just electric fields do not naturally cancel each other out or anything, okay? It just happens to be in this particular case. In fact, all I would have to say is this line is not infinite and we would be effed, okay? In terms of doing anything in this class. Okay, all sorts of bad things would happen. Okay, so, I mean, in terms of doing a calculation, nothing bad would happen. It's just like, it'd be really annoying to calculate this, do any kind of like sensible calculation, okay, for a class. All right, so now, so let's call this guy, because we're looking at, so what we're gonna do is we're gonna figure the effects of this guy, and the guy sitting next to him, and the guy sitting next to him, et cetera, et cetera. So what does that look like? And we're gonna sum all those together, right? And the nice thing is they're all pointing in the same direction, so it makes the vector summation easy, okay? And because we said the charge is continuous, instead of doing a summation, we can do an integral, okay? Which is the same as, integral same as sort of like doing a continuous summation. So that's where we get to this. So, and so each one of these guys creates an infinitesimal electric field in the y direction. So again, this thing is infinitesimally small. So it's going to give me an infinitesimally small electric field. By the time I integrate all these guys, it's going to be more, it's going to be a substantial electric field. And it's going to give me something else. Okay, it's going to give me, but for that tiny guy, it's going to give me a tiny electric field, and then I'm going to sum up all his brothers together with him, and we're going to see what we get. Okay, so that for that infinitesimal guy is going to give me the infinitesimal electric field. It's going to have a lambda dx of charge, so remember again. So electric field is Q over 4 pi epsilon naught 1 over r squared E sub r. Okay, so this is the Q over the 4 pi epsilon naught. This is the 4 pi epsilon naught. Okay. And then r squared, so this is r. Okay, remember I said this was a away from this line, a distance a. So I want to calculate this r, this is x, this is a, so it's square root of x squared plus a squared squared, or just, the square is going to get rid of the square root, and I'm just going to end up with that, okay? But I'm only calculating this guy. So this is going to be multiplied by cos theta, where theta is this guy. Because I'm only calculating, so that infinitesimal electric field is pointing in this direction, not this, dE sub y. dE sub y is the component of the electric field only pointing in this direction, okay? Just dE, the infinitesimal electric field, is pointing in that direction. But I know I'm going to cancel everything except this component with his twin brother, so I'm just going to calculate this guy. That's where the cos theta comes in. Okay, and cos theta is going to be a over a squared plus x squared. Well, how am I doing that? X squared plus a squared to the 1/2. Guys with me?
Yep.
So again, cos theta is that over that. Go ahead.
Why aren't you doubling the lambda dx if there's, because the way you're canceling it out
Yeah.
by having to.
Yeah. So the reason is, thanks for asking that question. So I was, at the moment, I'm just calculating the electric field for just this guy. And I used my description to explain why I'm only calculating in the y direction. So that factor of 2 comes in when we start doing the integral. But good question, yeah. So, but I was just kind of giving you guys, I'm just jumping back and forth, sorry. But, so, okay, so let's see what I want to say. Okay, so let me just write this so I don't confuse myself. Lambda dx over 4 pi epsilon naught, and over x squared plus a squared. Got the a over x squared plus a squared to the 1/2 here. And then to get the full e sub y, we need to integrate from minus infinity to plus infinity. We're going, x is going from all the way minus infinity all the way to plus infinity. We're going to sum up all these guys. So minus infinity to plus infinity, dE times y. And here's where because, sorry, I gotta start getting your names. What's your name? Bomta? Thanks, Bomta. So here, instead of doing minus infinity to infinity, I can do it from 0 to infinity times 2. Okay, because it's an even function. Okay, lambda dx over 4 pi epsilon naught. And got dx, what else do I have? And then I can combine basically this guy and that guy, and I'm going to get 1 over, well, a here, and x squared plus a squared to the 3/2. Okay, and then I can, let's see, I guess I can move in. I'm going to move these guys back here, get all the constants out of there. Whoops. Why am I doing this? I'm making you guys' lives harder. 3/2. I'm just going to copy this over. So I'm going to move a out here. I'm going to move a out here. I'm going to move lambda out here. I'm going to move 4 pi over epsilon. Basically, I'm going to put all the constants out here. Okay, so I'm just going to end up with this guy. Cool. So now we just got this little problem of solving this integral. Any ideas, thoughts? No.
Would it be easier if I take x squared plus a squared and change the sign of 3 over 2?
To do what, sorry?
So basically to do the integral,
Yeah.
so just take it up and change make it negative.
Oh, make it minus 3/2? It might, but I think you're still stuck with the same situation. What do you do with x squared plus a squared to the minus 3/2? Yes, yes. Any thoughts on what kind of substitution? I could spend the rest of my, by the way, this is a leading question, because I could spend the rest of my life trying to figure this out, and I would not figure it out. But it's a geometrical substitution, like you guys are saying. But anyway, I'm just making the point that, like, this is just, practice, doing homework problems, etc. I would not be able to tell you guys if I didn't know what I was going to lecture you guys on. Like, it's not clear to me what substitution. It's an integral we got to do. And now you're kind of in math doing integrals. And people have been noodling on integral for, I guess, for 3 centuries? I don't know. So they got these tables of integrals and techniques in math, and substitutions, like trig substitutions is one option. So that's what we're going to do. And because, to do integral 3/2, obviously it's kind of like, it's annoying. So again, I'm not like some integrating genius, whatever, just looking the stuff up. So what you want to do is X this substitution. Okay. All right. But there was, as I was looking into this, there is like a method to this madness, or I shouldn't say a method to this madness. Some like interesting nuances here that I thought I'd share with you guys, like in this substitution, because sometimes it just seems to me there's like a random bunch of like stuff. Oh, you got this, you substitute this, whatever. But one thing that I thought was interesting is, let's say if you pick the substitution like x is equal to a cos theta, let's say for the sake of discussion. Right? You'd be kind of hosed. And the reason for that is because you want to get, x has values from 0 to infinity. Okay? Notice a cos theta is not going to have values from 0 to infinity. Cos theta goes from 0 to 1. So basically you're limited. If you did this kind of substitution, x equal to a cos theta, like wrong kind of substitution, you would not be able to have the full limits of any integral. You would just be able to do that substitution for an integral like 0 to a, because cos theta doesn't span, a cos theta doesn't span all the way from 0 to infinity, whereas tan of theta does go all the way, does span the full 0 to infinity. So it makes it a good substitution. This is just sort of, again, like sort of a visual, maybe a little nuanced thing about how to think about these integrals and what we're doing. What we're doing for this is we're doing a substitution, but we want that substitution to allow us to span the full length of we're trying to be able to integrate over this entire minus infinity to infinity range. So when we're doing the we're doing the substitution, normally you could do any substitution you want, right? I just say, hey, like x is this, and I'm going to call it something else. But in this case, you also have this factor that you're trying to integrate that function. And if your substitution doesn't, it has to both be easy to calculate and allow you to get the full limits of the integral. So I don't know if that helps you guys, but that was like, whoa, that's interesting to me, as like what makes a good substitution, what doesn't. So just because something is easy to integrate doesn't mean it makes a good substitution. It also has to be able to live with the limits of your integral. Okay, so now we pick this. Why did we pick it? Okay, well, the dx, the rest of those dx, if I do dx d theta is a secant squared theta. Just as a reminder, secant of theta is 1 over cos of theta. Okay, so dx is a secant squared theta d theta. So I'm going to put everything in this form, right? E sub y is 2 lambda. So I'm going to rewrite this with all this goodies. Okay, substitute that. So 2 lambda a over 4 pi E0 it's going to go from 0 to pi over 2 a secant squared theta d theta over let's see, I have x here. So it's a to the 3/2. Am I doing this right? So x is a tan theta. Let me just do it Let me just not jump over any steps here. I'm confusing myself. That guy's side. So what's x squared plus a squared to the 3/2? So it's a squared tan squared theta plus a squared to the 3/2, right? Am I doing this right? What? Yeah, okay. So I'm going to pull out the a squared, 1 plus tan squared theta. Sorry, forget about this for a second. If you're just doing this guy. Let me start from scratch, sorry guys. Let's just look at this guy. Let's just focus at this guy. I'm not gonna stop jumping so many steps. So I'm gonna look at just this guy, okay? So x squared plus a squared with this substitution is gonna give me a squared tan squared theta plus a squared. So if I pull out the a squared, I'm gonna get 1 plus tan squared theta. Okay, and it turns out that this is secant squared theta. So that's equal to a squared secant squared theta. So I'm going to plug that guy here. So I'm going to have a squared secant squared theta to the 3/2. Everybody with me? I'm just substituting and sort of grinding through what these things mean. Okay, so, okay, all these guys, you know, now you got this a squared goes with this square root, this guy goes with that square root, so let me just do this. Very easy for me to confuse myself. So ends up this guy, whoops, this guy is gonna, that square root will kill that and kill that. So it'll be cubed. So this guy, so the guy will turn into a cubed secant cube, right, theta. And that gets canceled out with the secant squared a here, so we're just gonna end up with 2 lambda a over 4 pi epsilon naught. 0 to pi over 2. 1 over a squared secant theta d theta. Did I do that right? And so I can, this a is gonna cancel one of these a squareds. So I'm gonna end up with 2 lambda over 4 pi epsilon a, 0 to pi over 2, 1 over secant theta d theta. And so this is just 2 lambda over 4 pi epsilon naught a, 0 to pi over 2. So secant is 1 over cos theta, so 1 over secant theta is just cos theta d theta. So we're finally getting our payoff here with all this excessive amount of substitutions, 4 pi epsilon naught a. And so integral of cos theta is sine theta, right? So sine theta 0 and from pi over 2 are the limits. So it's 2 lambda, 4 pi epsilon naught, 1 minus 0, don't forget the a. So E sub y is, well, let me just do the amplitude of it, is 2 lambda 4 pi epsilon naught a. And the direction is always away from the line. Ah, man, I'm exhausted. I don't know about you guys. But, okay, so what is this? Let me just talk about what this means. Okay, so now, as we expected, there's some expected stuff, some unexpected stuff. Okay, so there's an electric field. One unexpected thing is this A is how far away you are from this line. So like again, if I draw this line, that's gonna poke my eye out, so this is kind of coming out here, right? So I'm looking at the electric fields as, you know, I'm moving distances away from it, right? So I'm looking at the electric field here, so this is like A, say, as A is changing. One surprising thing is that we're not dropping as 1 over distance squared, we're dropping as 1 over distance. So we're dropping much slower than a point charge. I mean, there's a huge difference between this 1 over distance squared, 1 over distance, okay? And the reason for that is we have, this is very, very like surprising, you're gonna see even more surprising stuff with other shapes, is because of this infinite line thing, okay? So that you're getting these contributions as you're going, it's 1 over distance, okay? Another interesting thing, I guess, is it true? Am I want to think about? So the other weird thing is you would think about it, why isn't it growing more? So that's the other way to look at it, right? It's either not dropping off as much, but as you're getting closer to the line, you're also not strengthening as much. Is that true? Is that another way to look at it? You guys see what I'm saying? Is if you're like a 1 over distance squared implies, you know, you're dropping off very rapidly as you're moving away, but it also implies that you're getting very, very strong as you get closer and closer, right? 1 over r squared, that r gets small, that 1 over r squared gets huge, right? So why, like I have an infinite line, so how come this isn't getting as strong as I'm moving closer to myself, okay? And the reason for that is, if you want to think about it, but it's just an explanation I have for myself, is as you're moving closer and closer here, okay, the electric field lines are getting strong in this direction and this direction. They're getting stronger, right? But this component, but they're getting shallower. Okay, so the amplitude is increasing, but the summation, because the angle is getting shallower, the E sub y is shrinking. Does that make sense?
Yeah.
So, and as you get further away, it's dropping, it's 1 over r squared is dropping, but the angle's giving you a bigger component in this y direction. It's kind of a visual, I don't know if that helps you guys, but sort of this is what the geometrical thought comes in there. Anything else I want to say about this? Okay, so that was that example of how you use electric fields. Vectors, again, I just want to make sure you guys, like, a big part of this class, I don't want to say integrals and trig and all this stuff doesn't matter as you're obviously you're like doing it here, and it's like quite annoying, but we really faked it to make it like simple, right? To like be able to do this. And pretty soon, I'm going to do 2 more examples. By the 3rd example, I'm going to claim I won't even be able to do it this way. And that's sort of the intro to Gauss's law, which sort of gives you a way out of this mess. Not a mess. Out of this way, method of doing things. Gives you another tool. Okay, ready for a break? Yes. Okay, guys, so it's 9:35 How about a 10-minute break and we do 9:45? That sound good? Funny, like some of you guys had pictures, like I didn't recognize you, Louis, from your picture. Actually, I saw your video last semester.
What video? Oh, yeah,
Where
yeah,
you would sometimes come online.
yeah.
Yeah. The rest of the class was, and some guys have
It's
pictures.
actually
and
last
stuff.
year, not last.
Was it last year
Yeah,
already?
that's-
How long ago was it?
When we took the
Was it like spring?
2200.
Yeah. Was it spring of 21?
Yes.
Wow. Feels like it was last semester. No. Ugh. So when are you gonna graduate?
I started a minor in economics, so
Ah,
it's just gonna take me a little bit more. But maybe next year.
cool. Glutton for punishment, huh?
What?
I said glutton for punishment, you're adding more stuff.
I
Nice. Oops. Plug myself in. Are the rest of you guys juniors, seniors? What are you guys? Seniors? So the senior means like graduation, or it just means the fourth year? It's typical. Is it on app? Mostly people graduate in 4 years, or mostly like it's longer?
I don't think it's possible in 4 years anymore.
Yeah.
Yeah, at the freshman education study, it's like 4 to 5 years for our.
What's that?
It's like 4 to 5 years for our program.
Yeah.
They tell us that.
Says you have to go so far in math, and then you have to do all your engineering courses as well. And you're basically getting 2 degrees in one.
Yeah. Simultaneously charge.
Professor, did you say you worked at JPL?
Did I? Yeah, I worked at JPL like in 94, 95 type frame.
Did you like it?
Did I like it? I absolutely, positively loved it. It was like the best time of my life, practically. Hmm?
Who did you work with?
I worked at, so let me tell you a story about JPL and working in big companies and who I worked with. So I got my I'll just give you the long version. So I did my grad school studies and PhD program, in case you guys want to do your PhD. For whatever reason, people ask me for advice. I think it's the gray hair, so I talk to a lot of PhD students. So I have to have a canned story. So I did my PhD in optical networking back in the 90s, when things were pretty limited. So it ended up being a very although I was doing device physics and doing sort of building stuff that you can drop on your foot, I never believed in it. A year into my PhD program, I was like, this shit's not going anywhere, right? Just to be good for a PhD. And it was really a hot area compared to quantum computing now or something like that. And just going, God, this thing's come on. I'd already been in the industry. I already was doing chip design before I go to grad school, so I had some inclination on what it would take to replace. This was we're going to replace semiconductor chips, interconnects with optical interconnect. I was like, really? With this thing? So anyway, after that, I was like, man, I'm gonna kill myself if I don't do something practical now. But then I wanted to put research and, do some research for a couple of years after you get your PhD before I went to the industry. So I said, so I went and listened to a talk. I just happened to be at a conference. I heard a talk from who turned out to be my boss. It's a gentleman named Eric Fossum, who's now at Dartmouth. And he's kind of known as the father of this technology that then I started working on and took off from there. And it was like the second best decision I made in my life, just sitting in that thing. And then I just called the dude up and I'm like, man, I gotta work for you, like what it's gonna take, whatever, sort of insert myself in his group. And basically the reason for that was because I could recognize something that was like in R&D, but you just somehow I could tell it was coming. Like, I didn't realize how long it would take, which I just thought it would be like a year or 2 years away, so it'd be this cool experience of working in something in the lab and then getting into products and stuff like that. And it ended up being exactly like that, except it just took longer. But anyway, I worked there for a year and a half. We were in, I forgot what the group was, but anyway, he's no longer there. But we were building, I want to say 3,000 or something, so it was. But we were doing R&D, and then what happened is he left, started a startup. I joined his startup, and that's where I left in a year and a half. But that year and a half, I just loved it because I was single, and it was this brand new field. I was single and frustrated from working in too theoretical of a thing. And man, it was just like everything you touched in this field at that point was like, it's all easy pickings. Everywhere, it was just like blowing up. So I'm coming into this field, it's blowing up under me. So anything I touch is a paper, is like a new discovery. Everything. It was just, and like the first week I showed up there, he's like, oh, you gotta come to this conference. But that happened to be local. I was like new to this field, right? Was in an adjacent field. Come in there, at this conference, expecting like a normal, I don't know if you guys have been to technical conferences, expecting sort of like a staid gentleman speaking. It was like a frickin' war in this conference, okay? And it was this guy's group against the rest of the world. So there's like 150 people in this workshop, working in big companies back then, and everybody was against us. And it was like war. It was like 6 of us from this group, because what was going on? The incumbent technology was, at that point, was charge coupled device CCDs. I don't know if you guys heard about it. Some imaging stuff that was incumbent. This guy, Eric Fossum, was saying, here's this new technology that I think is gonna kick your ass. Like, and he was like very bold. He's like really good at like marketing, branding, whatever, making bold statements. And these guys didn't like that at all. So I was like, man, this, I haven't had this much excitement for, single, wanted to do something new. So by single, I mean like 60-hour weeks, nobody to go home to, happy to be in the lab. So just good stuff. So that's the great part about JPL. And so it was just amazing. Like my parents live in San Diego. So some weekends I'd go to San Diego. I kid you not, I couldn't wait for Monday to roll. Like I was like, Sunday afternoon, man, I'm gonna be back. So I gotta get more goodies. It was so exciting. But then the JPL also, because I know lots of people who hate, I was actually talking to friends that work there. So lots of people don't like it at all. Because even when I was there, there's so much bureaucracy. You're part of Caltech, you're part of you're getting funded by NASA, there's a lot of bureaucracy. So I think I joined JPL and maybe 3 or 4 months later I had a computer. The rest of the time I brought my own laptop to work, it's that kind of thing. And you can't even, everybody's really nice, everybody's really, the people in the bureaucracy, but you can't, they're just inundated. Yeah, there can be a lot of, there's a lot of, like any other big company, there's a lot of politics. So long story short, it really depends, in big companies, it really depends on the individual you work with. Okay, so I really liked the person I worked with, Eric Fossum. Not because he was a nice guy. He's my mentor, I love him. Second father, whatever. but especially at that time, he was a flaming asshole, okay? And he would be in, like, almost fist fights with people in the lab, strong personality. But basically, nobody would mess with me as a first, you know, as a green guy, because they knew I was this guy's boy, so, like, you know, that's that guy, right? So that was good. I was like really isolated from lab politics, because he was fighting all the battles. Because I was putting in hard work, he liked me too, so I was also like, he'd leave me alone to do my thing. So that was great. I really liked it, but you just gotta go with all those caveats. But I just had, it was like, man, I did a lab, I live right next to, I could walk to JPL from where I live. So I just happened to do a lab tour a couple of years ago, and that was
Did you
before
go
the
to
pandemic.
MDL?
What's that?
Did you go to MDL?
Was it working in MDL? I worked at a building right next to MDL.
Okay.
So we worked with the guys at MDL a lot, but we were right, I forgot what it was, but
300.
yeah, I think it was 300, right, so. Yeah, I was getting goosebumps walking around there, looking at my office, I had a great time there. But it was also both really, I mean, I wouldn't have wanted that job as a married guy, let's say, from a work standpoint, but that's not the same as every job there, but I also wouldn't want to deal with that bureaucracy. I wouldn't want to deal with a boss that I didn't really like. So I was just, my advice is if you're thinking about working there, first of all, I had a great time. But think about specifically who you're working with. And then the sense I got from JPL and the sense I continue to get is it's very PhD heavy. It's really like working kind of like in a university. So to some extent, I don't want to overemphasize this, but to some extent, you're sort of a second-class citizen if you're not a PhD. If you're not a PhD, you typically can become the PI, the principal investigator. You're not leading, you're kind of doing stuff. But there's lots of cool stuff, lots of cool people. So I guess mixed,
I
you know.
currently work at MDL.
Oh, you do?
Yeah.
Who do you work for?
My group soup is Frank Greer.
I don't know.
Before him, it was James Lamb.
Mhm.
And then I think the directors are Robert Green and someone else.
Huh.
But the people I work with, a lot of them, I mean, besides the really higher ups have PhDs and whatnot.
Yeah,
But some of the people I work with do have bachelor's degrees.
yeah,
And I was gonna ask, like, they've seen, like, they've been working there for, 20, 30 years.
yeah,
And they've had growth,
yeah.
but they're not, they're not group supervisors. Whereas Frank, I think he's been working there for maybe 20 years, but he became group supervisor last year, or
Yeah.
just a couple months ago, I guess.
Yeah. So it just depends on you, man.
Because I don't want a PhD, so that's why.
What? No, I'm just kidding. Yeah.